Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give an example of how to apply Newton's second law to a system containing multiple parts and to demonstrate how to draw different free bodies of those parts. So in this example here, imagine this person here pushing on that pair of very large boxes full of, I don't know, bananas and apples or something. And imagine that person pushes with a 200 Newton force. And what we're going to try to calculate here is the force between these boxes, right? Now, before we do that, I want to throw in a couple of assumptions here. One, I'm going to assume that the force that person applies is constant, and I'm also going to assume that there's no friction between these surfaces. And again, are those assumptions realistic? Well, not really, but they're, I'm doing this to make the example, relatively easy to follow. The purpose of this problem is not going to be how do you take friction into account. The purpose is how do you draw the different types of free bodies. So I'm trying to give a reasonably simple example to demonstrate the purposes I want to demonstrate. All right, so a really important thing to recognize is that what your free body looks like is going to depend on what your system is of. If I draw a free body of this box, right there, it's very important to recognize that there's a contact force here between these surfaces, and we're not going to know what that force is. Doesn't mean we can't draw the free body, doesn't mean we can't write equations for it, but the equation is going to have an unknown force and an unknown acceleration. Another option is to draw a free body of this part of the system. However, again, we have a surface in contact. That's going to give us an unknown force, and we don't know the acceleration. So that's going to have two unknowns. I would suggest starting with a free body of the entire part of the system, the whole thing. If our free body is of the entire system, the 10 and the 40 kilogram mass together, the force at that, let's do that in red here, the force interaction here at that surface is an internal force and therefore will not show up in the free body. So I would strongly suggest a free body of the entire system. So what I'm going to do here is, if I can do this, I'm going to just copy that system here. And paste it here, right? Oops. To do the free body. Right? So a free body of this part of the system might look something like this. I'm going to go ahead and use nice straight edges for my free body. All right, so we know that this person is applying a 200 Newton force horizontally on this box. So we might represent that with a force vector, right? And label it. We could label it either F or 200 newtons because they're equal, right? We know that each of these boxes has a weight. Now we actually have a choice. We can put them separately, or I'm going to do this. I'm going to draw one gravitational force acting at the center. Right? Gravitational force is down, equal to mg. Now technically it doesn't go right at the center, and I'm going to talk more about why that is later in the course, but you typically put gravitational forces at the center of mass, which in this example should be more to the right. It's not going to be relevant for this example, so I'm just going to move on. We'll talk again later in the course about where that gravitational force goes. All right. Another very important thing to realize is that along this surface right here, we have a contact between the ground and the boxes. So we need to draw a force vector for that. And that's an example of what we would call a normal force. We could draw two separate normals, or we can think of them as just one individual normal force. I'm just going to think of it as one normal up. Keep in mind that that normal is the sum of the two. All right, so again, I've got a single mg, a single normal. This m now, though, because of how I've defined my system, I'm going to put a little note here, is 50 kilograms. Okay. If there were a frictional force, it would be acting along this surface. Oops, let me show it. It would be acting along this surface right here, and it would be to the left. But again, I assumed no friction in this example just to keep it as simple as I could. All right, so there's our free body. Now we can apply Newton's second law, which says net force equals ma. Now by net force, that means sum of all forces equals mass times acceleration. Now Newton's second law, again, is what's called a vector law. That means you apply it in directions. My standard rule of thumb is to identify the acceleration direction, call that positive. This system obviously is accelerating to the right, so I'm going to call right positive. So as I look at this, the three forces that we have, only one of them is in the x direction, this one. So the net force is going to be 200 newtons equals m. Now the mass of that system is 50 kilograms, and then times a, the acceleration of the system. This equation can be solved for A. You get 200 newtons over 50 kilograms, which is numerically equal to 4. Now, unit-wise, remember that a newton is a kilogram meter over second squared, and that's over a kilogram. So, unit-wise, we get 4 meter per second squared. So as we find things, I suggest we, write them down somewhere. We know that the acceleration of the system is going to be about 4 meter per second. All right, now, how do we use that now to find the force at that intersection there between those two? So now what we want to do is draw a free body of a piece of the system. We could either do the 10 or the 40. It doesn't really matter. I'm going to go ahead and do the 40, I guess. So what I'm going to do here is see if I can just kind of copy it and get it out of there, right? So what you would do on your paper is you would just redraw it, trying to make this look as pretty as possible. So what I have now is I have kind of a picture of my 40 kilogram object, and now I'm going to draw a free body on it, of it. Now, again, at this surface right there between them, there is an interaction. There's going to be some sort of normal force, and that normal force is going to be to the right. Oops, I'm going to draw that in black. To the right on the 40 kilogram object. Right? That's the normal. We could call it something like maybe normal 1, 2, the normal force between object 1 and object 2. If I were drawing a free body of the 10 kilogram mass, that normal would go to the left. Right? Now, here's another surface in contact, so there's going to be another force. That force is going to be up. Oops. Up. That's the normal between object 2 and the ground. If you want to put the subscripts in, you don't have to. These are different normals. They have to be distinguished in some way, that they're not the same. But all right, we got a gravitational force down. I'm going to go ahead and put that in there, mg. And again, whether you draw the gravitational force like it's pointing at the mass or coming from the mass doesn't matter, right? Either one is just fine. And those are the only three forces acting on this mass. So we can go ahead and write a Newton's second law equation now. Sum of all forces in the x direction equals ma, calling right the positive x direction. And again, we look at our free body here and we note that there's only one force in the x direction, that guy, the one I called normal 1, 2, and that has to equal m. Now the mass of that part of the system is 40 kilograms. The acceleration of the system is known at 4 meter per second squared, and out comes 160 newtons. So the normal force between these two should be 160 newtons. I'm going to leave this as an exercise to the viewer to demonstrate this, but if you draw a free body of this part of the system, you will have the 200 Newton force applied to the right. You would have an unknown normal force, the one I called normal 1, 2, except you would draw it to the left. When you write your Newton's second law equation, you're going to end up with 200 minus the normal equals m times a, and if you solve for that normal force, out should come 160 newtons. So this is just meant to be a relatively simple video on how to draw free bodies at different parts of a system and how to apply Newton's second law. Hope it helped. Have a great day.